So the final talk of the conference is given by Bianca, Marin, and Moreno, and it will be about the mean field analysis of an incentive algorithm for closed stochastic network. So please, Bianca, go ahead.
So first, thank you. It's a great opportunity to be here, and also thank you, Mark, for the whole week. It was amazing. So as your last talk, I'll be presenting a conjoint work done with Philippe and Hanene Mohamed that are here today, and Trépanier and Amaury.
Sorry. Okay, try again. Sorry.
Okay, thank you. So just a few words about what we're going to present today. So our goal, what motivates us, is to study an incentive policy for car distribution in a car sharing system that exists today in Montreal, implemented by a company called Combinatorial. To do this, we are going to, motivated by an extensive work of data analysis, to build a stochastic model homogeneous in time and space that is going to allow us to do a Markovian analysis and mean field approximation that, in the end of the day, is going to allow us to study the steady state behavior of the system. So now let's define everything. So car sharing system is just a transportation system where usually companies are going to make vehicles available for people to rent them for a short time to do their trips. And usually this can be done in two ways. The station-based way, where companies are going to have stations where the users can go take the cars and they have to finish their trips in the same station. And also we have the frequency system where the cars are spread through the town, and then the user can end their trips wherever they want inside a certain limit of the town, of course. So we have here that this frequency system, it allows a lot more flexibility. However, this comes with a price because it does not guarantee car availability for the user where they want or when they want. So companies, they do what we call vehicle redistribution to try to solve this problem, which is basically to relocate the vehicles where they are most needed, which is usually the most crowded region of the city. And this can be done in two ways: an active way, where the company is going to hire drivers to do this service, and a passive way, where the company is going to do incitative policies for the users, so that they themselves, the users, are going to do this relocation. So this is our goal, is to study an incentive policy implemented by a company called Combinatorial in Montreal, that here we are going to call it the gift policy, that I'm going to explain why. So a brief introduction to the gift policy. Combinatorial divides Montreal in two clusters. The intensive cluster, circled here in red, that is the most crowded region of the city, and the normal cluster, that is everything outside of the intensive cluster. Here we have the app of Combinatorial, where the user can find cars that they can take for a trip. If a car is parked outside of the intensive cluster for more than 16 hours, this car is going to start appearing with a small gift above it. If a person takes this car and finish their trips inside the intensive cluster, they are going to get a 33-minute discount on the trip they just made. So it's an incitation for people to take cars that are parked for a long time outside the normal zone to the intensive zone, that is the most crowded region. So just to be clear, every time now that I say a car, I mean a normal car. And every time that I say a gift, I mean the car with the gift above it. And just to resume, we have two criteria for a car to become a gift: to be parked for more than 16 hours and to be parked outside of the intensive zone. And we have one criterion for the person to get the 33 minutes discount, that is to finish the trip inside the intensive cluster. So as I mentioned, we had an extensive work of data analysis that motivated the model that I'll be presenting. The data is from October 2019 until October 2020, and we decided to not consider the 3 months of COVID. These are data from all the transactions of the pre-floating service. So we have approximately 1 million transactions done by 146 vehicles. And some of the interesting results of our data analysis concerns the shortage of gifts. So let me explain. We have in average 3,500 transactions per day. From these 3,500, we have in average 47 that are done by gifts during winter, and 86 that are done per day by gifts during summer. And we can look at the gifts that are being used, and by that I mean the gifts that are being used for the relocation purpose. So a person can get a gift but not finish their trips inside the intensive cluster. And a person can get the gifts and finish the trip inside the intensive cluster and get the 33-minute discount. So we can see here that from the average 47 gifts per day during winter, only 15 are gifts being used for the redistribution purpose. And during summer, from the 86, only 30 are being used in average for the redistribution purpose. So we can see that it's very hard to see the impact of gifts in the user's behaviors because we have very few gifts and even fewer gifts used for the redistribution purpose. Also, we also saw that we have very few people adhering to this gift policy. So more than 90% of the people never use the gifts in their lives. So it raises the questions, maybe this policy could be more effective.
Just repeat what the difference between few gifts and few gifts.
Of course. So the gifts is when the car.
Yeah, because few gifts means that they don't appear on the app.
It means that there's no gifts appearing in the app. So probably it's because we don't have cars that stay parked for more than 16 hours. Yes, outside the intensive cluster. And the gifts used are the gifts that are being relocated to the intensive zone. So this raises the question, could this incentive policy be more effective? Maybe for bigger incentive, maybe for less time for a car to become a gift. This way we could have more gifts in the system. And all of this data analysis work motivated the model that I'm going to present right now. So first of all, I need to define what is a station. And here, a station is not the same as the station-based system that I mentioned in the beginning. Here, for the mathematical purpose of the model, we had to divide the region of Montreal in small squares of 1 kilometer squared that we decided to call stations. So we are the free floating service, and suppose that here is the free floating area of Montreal. We have here in red the intensive cluster that from now on I'm going to call the cluster 1 that has 28 kilometers squared. So you're going to say that it has 28 stations. And the blue cluster here, that is the normal cluster that has 72 kilometers squared. So we are going to say it has 22 stations. And now I'm going to explain how the model works. So as I explained, we divide the city in two clusters. Cluster 1, the intensive cluster, cluster 2, the normal cluster. Each one has a certain number of stations, and 1 for cluster 1 and 2 for cluster 2. And each station has a certain capacity. That is the maximum number of vehicles that can be parked in the station. And we have K1 for stations in cluster 1 and K2 for stations in cluster 2. A person arrives in a station in cluster 1 following an exponential time of parameter lambda 1. And the same for a person arriving in a station in cluster 2 with parameter lambda 2. And we say that lambda 1 is bigger than lambda 2 to represent the fact that there are more people arriving in the intensive cluster, is a more dynamical place. If a person arrives in a station in cluster 1 and it has no cars, the person just leaves the system. If a person arrives and there is at least one car, the person is going to get this car and is going to do a trip with this car. So here we have the node of cars making trips. The cars making trips also follow an exponential law, now with parameter mu. When the trip is over, with probability C1, the car is parked in a station cluster 1, with probability C2 in a station cluster 2. If the station is already full, then the car just goes back to making a trip. It's similar for a station cluster 2 with a little detail. Cars in a station in cluster 2, they have a clock that also follow an exponential time of parameter delta. And if this clock rings before this car is taken for a trip, this car becomes a gift. If a person arrives in a station that has both gifts and cars, the person takes the gift with parameter p and the car with parameter 1 minus p. If the person takes the car, then the same is going to happen as before. If they take the gift, they are going to make a trip with this gift. So here we have the node of gifts making trip. And this is also going to follow an exponential law, now with parameter mu c. And with probability q, they are going to park in the intensive cluster, the cluster 1. And with probability 1 minus q, they are going to park in cluster 2. Of course, if a person arrives in a station that has only gifts, they take the gifts with probability 1. If it has only cars, they take the car with probability 1. And if it's empty, they just leave the system. And also, it's important to say that once the gift trip is over, this gift is parked as a car. So we have this change of classes both here in the stations in cluster 2, and in the end of a gift making a trip, it is parked as a car in a station. And also we consider the model to be homogeneous inside each cluster, and we don't distinguish cars making trips. So the goal of this model is, as already said, to understand this gift policy, to compare this case with no policy to see if it's really helping the redistribution of the vehicles or not, to investigate the influence of parameters. So, for example, the time to become a gift, there is represented by the rates delta, the proportion of gift users that is represented by the probability P that a person is going to take a gift over a car when both are available, and the probability Q that this gift is going to be parked in the intensive cluster. So it means the gift is being used for the redistribution purpose. And also the fleet size, that is the number of cars and gifts in the system. Our performance criteria will be to look at the proportion of empty or full stations. And why? Because maximizing this avoids having a person arriving in a station that is empty. So it's going to maximize the number of transactions. So in the end of the day, it's better for the users and it's better for the company. So if it's not clear yet, you can also have a queuing interpretation for this. So this model can be seen as a closed stochastic network with two types of nodes. The first type of nodes are one server nodes with finite capacity that are RO stations, RON stations, that is the sum of the number of stations in each cluster. And the second type of nodes are infinite nodes that are exactly the routes linking the stations with the both the stations. And that is exactly the nodes of cars and gifts making a trip. As already said, all the service times are exponential, and we have a fixed number of customers in our system that are the cars and the gifts. So we have two classes of customers in our system. However, this is not a Jackson network because of the transition of classes between cars and gifts. These additional transitions, they make this problem a lot more complicated and also a lot more interesting. So having cars in station 2 becoming gifts and having gifts in the end of their trips being parked as cars, this is what makes it different than the normal scenario. So now let's go to the mean field analysis. For that, I'm going to define some variables. We have here first, xji is the number of cars at station I in cluster J. Ci is the number of gifts at a station I, and it's necessarily in cluster 2 because we only have gifts appearing in the normal cluster. And R is the number of gifts making a trip. As I said, the number of cars and gifts is fixed, so this is enough to give us the state of the system. And it is a Markov process. As I also mentioned, this model is homogeneous inside each cluster, so it is sufficient to look at what is happening in a station in one of the clusters, which means that it is sufficient to look at the empirical measure process that I'm going to define here. So first, we define this variable y1k that gives me the proportion of stations with k cars in cluster 1, and the variable y2k line L line that gives me the proportion of stations with k line cars and L line gifts in cluster 2. And with these two variables, we can define the empirical measure process y. Remembering that we have a capacity of cars both in station 1, so we have maximum k1 cars per station in cluster 1, and the same, we have a maximum number of cars and gifts that can be parked at the same time in station 2. And our goal will be to understand what happens when the number of stations gets large. So we need to know how to write the drifts of our process, and for that we need to know how to write the transitions. So here we can have three different types of transition. So given a state y, we can have a transition because of a user arrival, because of a car becoming a gift, or because of a car or gift being parked. Here I'm going to give an example of how we write these transitions, and the other transitions, they are just written in the same way. So for example here, let's look at a user arrival at a station of cluster 1 with k cars. So if k is bigger than 0, then the person is going to take a car for a trip, right? So we are going to have the number of stations with k-1 cars increasing and the number of stations with K cars decreasing. Here the proportion, I mean. So, and here we can write this with the symbol E that we chose to be the canonical basis that we had to write to have our transition. So here we have the transition from a state Y to a state where we have a user arriving at a station of cluster 1 K cars and taking this car. And to have the rate of how of this transition, we remember that Y1K gives me the proportion of stations in cluster 1 with K cars, and as N1 is the number of stations in cluster 1. This gives us the possible stations, and lambda 1 is the rate of arrival of a person in a station in cluster 1. So if we multiply everything, we have the rate of this transition. And as I said, all the other transitions are written in this way. And our goal is to understand what happens when the number of stations gets large. And we have a standard theorem that says that when the number of stations get large, this process is going to converge to a deterministic equation that is the solution of a fixed system of ODEs that can be written like this, where Li is explicitly given exactly because we were able to write the drift part of the process. And also Ly can be seen as the generator of the Markov process. And the proof of this proposition, basically, it consists on knowing that we can write a Markov process as the sum of a drift part and a martingale. We can also prove that this Markov process here is tight, and so it has a limit solution. And we can show that when the number of stations get large, that the martingale part is going to converge to 0. So it gives us that this is going to converge in distribution to the solution of a system of ODE. So our goal is to investigate the steady state behavior of the model, which is the same as finding the equilibrium point of this ODE, which is the same as finding the invariant measure of this generator of the process. Just to remark, in the no-gift case, imagine the same case with the homogeneous model with 2 clusters, but with no change of classes. A work done by Philippe and Mohamed in 2012 has already proven an explicit result for this problem. But for the gift case, things are more complicated exactly because of the change of classes. So just remembering here, R is the number of gifts making a trip. We know that it is an infinite queue, so we know the format of the invariant measure. For a station at cluster 1, things are also easy. It is a finite capacity queue with capacity K1. So we also know the format of its invariant measure. However, things are more complicated for a station in cluster 2, exactly because of this change of classes. So we have this parameter delta that makes the change of classes between gifts and cars appears. And this is not a classical framework. So we don't know a closed form expression for Y2 bar. So this is probably going to say more to you than it did to us. It's not our domain, but we try to make an analytical method to solve this problem by using generating functions. So here, just for the sake of simplicity, we suppose that the capacity of a station in cluster 2 is infinite, and we look at P, the invariant measure. And what we wanted to know is if writing the balance equation for P, we could arrive at a functional equation of this format. However, we only managed to arrive in a functional equation like this that has this term for the first derivative of the generating function in the variable x. That it's not the classical framework, and as I mentioned, this is not our domain, so this probably speaks more to you. But for us it was a difficult framework. We didn't manage to solve it. So what we did instead was to do a numerical solution, because we are able to write the mean field equation, and to validate this numerical solution by doing simulations of the true Markov process that we are also able to write. And this is what I'm going to show right now. So all the parameters here, they are obtained from the data. So the rate of arrivals, the trips and cars making a trip. And as I mentioned in the beginning, in Montreal, for the real system, the threshold for a car to become a gift is 16 hours. But as here we are supposing that a car becomes a gift following an exponential law of perimeter delta, we take 1 over delta to be 16 hours. In this example, we take P equal Q equal 1. So just remembering, P is the probability that a person is going to choose a gift over a car when a gift is available. Q is the probability that a gift is going to be parked in the intensive cluster. So here we suppose that we have a perfect gift policy system. So everyone takes gifts and everyone is going to relocate the vehicle where we want it. And then we also have the number of stations and the capacity. So what we're going to look at here is in the x-axis, we have the mean number of cars per station. In the y-axis, we have our performance criterion that is the proportion of empty / full stations. In red, we have the case, we have the cluster 1, and in the bluish colors, we have the cluster 2. And here these curves are the numerical solution. In crosses, we have the simulation, so we can already see that the simulation seems to work well with the numerical solution. So it already validates that our mean field approximation seems to work well. And well, we also make the distinction between the case with gifts and no gifts. So what is interesting to see here, for example, is for cluster 1, let's take between 10 to 20 cars in average per station. So we see that the case with no gifts, we have a very high proportion of empty / full stations. This is probably because station 1 is the most crowded region of the town, cluster 1, I mean. So we have more people going there and taking cars, and we have a bigger problem of this station being empty, of stations in cluster 1 being empty. However, we see that in the case where we have a perfect gift policy, so we have people relocating vehicles from the normal zone to the intensive zone, this proportion of empty stations is much lower. So we see that the gift policy really seems to help our performance criterion. And finally, here in green is the mean number of cars per station for the company Combinatorial. And we can see here that in the case, if they had a perfect gift system, they would still have place to increase their fleets without harming their system. They would actually be helping the performance of their system. So that's what I wanted to say today. Our goal was to study an incentive policy for a car distribution in Montreal, as mentioned in the beginning. We had an extensive work of data analysis where we saw that this policy for Montreal had very few gifts and very few people using the gifts. And this data analysis also motivated our work. We made a stochastic model homogeneous in time and space that we were able to do Markovian analysis and a mean field approximation that allowed us to do a numerical solution and to validate it by simulation that allow us to understand all the influence of the parameters. However, we do know that our model has limitations, and one of them is, for example, our model does not consider temporal inhomogeneity of arrivals and returns. So we suppose that during the day or during the night, the arrival of person taking a car is the same, which we know is not. So this is one of the works that could be done. We talk a little bit about this in the article. And that's it. Thank you.
Thank you very much for that nice talk. Are there any questions?
Sorry, this is a small question. And just make sure that I understood the summary of the results. You said that Mohamed has a symptomatic policy that they've been running for 2 years. The data analysis shows that it isn't really useful to them at all. And so what you're trying to determine was, is it a bad idea or is it implemented incorrectly?
Yes.
And so assuming that it actually works, you show that it really shapes the traffic immensely. And so the conclusion of sort of this analysis is that it's not implemented well. Like maybe the users don't see it or don't know about it or won't know about it in time or don't realize how to take advantage of it.
Exactly. That's it.
It was a great talk. Thank you so much.
Any other questions from the audience? Or do you have another one?
Okay.
I have, this is a very interesting one. So I was wondering if you talk about like adding to the gift policy, say,
But they would not be able to.
yeah, so this is very interesting. I was just wondering, have you ever thought about adding to the gift policy an overcharge. And
Yeah.
then, yeah, I think we might have some impact.
But what is exactly the question to take this in consideration?
Yeah, so like, so website right now there is just the data policy.
Yeah.
I was saying maybe they could be combined with the overcharge policy. So if you have the car from the Pentagon and return to the Pentagon, then the overcharge, and then you have the car from the Pentagon to the normal, like normal price.
Okay.
Something like that.
Okay, we didn't think about it, but it's a really interesting point of view, actually, for Christina and Annette. I think this will be interesting, an overcharging policy, yeah. Yeah. So yeah, thank you so much.
Another question, is there a question online?
Maybe.
Very good. So thank you very much for the very nice talk. I'm going to pick it up at 5.